Hello and welcome to OpenCVBasics. George here. This is the second video in this series where we're going to look at actually visualizing the DFT. Now this is a two-step process and will require two videos. In the first video, we're simply going to set up the image so we can actually see it. In the following video, we're going to talk about recentering the DFT. Now, I want to go ahead and take everything I had previously done and place that into a new function. That way we can get it out of our main function. So let's go ahead and create a, void take DFT. We are going to pass into this function, of course, a reference to a mat object, which is our source. We're going to do a mat reference destination. And all we're going to do here is we're going to copy and paste our information. So we'll go from the DFT up past the merge, past the original complex, all the way to probably right here. Paste that in up here. Make sure we change our original float now to the source. And of course at the end, make sure that we set the destination equal to our DFT of original. All right, simple enough. Now we've gotten all of that code out of here and we can just make a call to DFT. Take DFT. We're going to pass in, of course, the original float now. And we need a new mat DFT of original. We'll keep that one. And that'll be our output. Perfect. Oh, sorry. One last thing we need to change. Up here, original float.size needs to be source.size in this case. All right. Now, we're exactly where we left off last video, just a little bit cleaner. So now we're going to create a new function called void. Show DFT. And the idea was we're going to pass to this the DFT mat object, source. And within here, there's a few things we need to do to visualize the DFT. Now, we have a two-channel mat object coming in, and those two channels correspond to the real and imaginary components. What we need to do is split that back up and remove the two channels because we're going to use both channels in visualizing the DFT. So the first thing we need to use is the split command. But before we can do that, we actually need to set up an array of size 2. So let's do mat split array is equal to, of course we're going to initialize both parts here, mat : zeros, just like before. We're going to use the source.size. And we are going to use a CV_32F type. For the second element, it's also mat : zeros, source.size again, and of course CV_32F. If I spell it correctly. Now we're ready to split it. So we'll do a split. It's not a splot, but a split. Our input matrix is going to be source. And our output is going to be split array. So hopefully you can see here that we are bringing in the DFT object as our source, and that has two channels. And what we're doing is splitting it apart and putting each channel into split array. The next thing we need to do is take the magnitude. Just like when dealing with vectors, it's going to be taking the real component, squaring it, and adding to that the imaginary component, which is squared, and taking the square root of both of them to get the true magnitude. This is easy. Let's first declare a mat DFT magnitude, and then just take magnitude, pass in the input, which is going to be split, it's not splot, split array, 0 as the first element, and then split array, 1, and finally, where we're outputting this information, which is going to be in DFT magnitude. Now that we have the magnitude, we need to finesse the values a little bit. The values are over an enormous range. We actually need to take the log of those values first to make everything work properly. But before we do that, we need to add 1 to every value to make the log function properly. So let's do DFT magnitude plus equals scalar : all, and then a value of 1. So that's going to add 1 to every single element in that object. Next up, we need to take the log. So let's do log. Our input is DFT magnitude, and we're going to have our output also be DFT magnitude. So we're keeping it all in that same variable. Finally, we need to normalize this thing. So let's just call normalize. Now the values, the ranges on this are all over the place. Like I said, even after taking the log, while they're now a little bit easier for us to visualize, they're still, the values are still well beyond 0 and 1. And that's all we're doing here is renormalizing that range. So we're going to do our input magnitude. Our output is also going to be DFT magnitude. Now we specify the min and the max value, which is 0 and 1. We specify how we're normalizing, which is going to be CV underscore min max, from the minimum to the maximum. And it's that easy. So let's go ahead and show this. IM_show. Specify a window name. We'll just call this the DFT, and it's going to be DFT magnitude. And of course we need to use wait key so that the program stalls and lets us see what's going on. Or not stalls, but it goes into a loop until we press a key. So now all we have to do is run. So let's call this function show DFT, and that's going to be DFT of original in our main function. Run it. Please build it. And there it is. There's our DFT. Now this is going to look different than what you probably expected or what you may be seeing in other textbooks. There's one step that we've missed here, and that is recentering this DFT. Follow me in the next video to figure out how to swap this so that you actually have the low frequency information in the center radiating outwards to the high frequency information in the corners.